Hey everyone, welcome to the MSD-RAS Introduction to 3D Programming. This is Patrick Danahy, your instructor for this 2-week introduction course. I'm going to start this introduction series with an introduction to the Rhino interface and some basics of 3D modeling. Once open, you'll notice that the default setup inside of Rhino's interface is a 4-view setup, where the upper right is a perspective view, and then the other 3 are 3 different parallel viewports. So top view, front view, right view. If you click on this arrow, you can change any of these. So set view, and then you can change this right view to a left view, bottom, top, perspective. You can also double click into any of these views. So double click on perspective. We now enter the perspective viewport. To navigate throughout this viewport in 3D space, you can right click, hold and rotate to orbit. You can hit shift, right click to pan. These are the perspective options. It's slightly different in parallel. And then you can scroll in and out with your scroll wheel to zoom. If you get to a particular view that you want to save and you want to come back to that view instead of the base perspective view, then you can go to this tab on the right for named views. If you don't have this in your toolbar, then you should be able to go to tools and then find the named views toolbar there, or click on this drop down arrow, set view, and then click named views. So if this is the view you want to capture, you can just hit the save icon to the right and then name it whatever you would like, and then hit OK. And that view will save there, and it renames the viewport to that view name so that you can later click on that to come back to that view. In the parallel viewports, instead of rotation for these, since they're elevational or for 2D viewports, you can just right click and it will auto confine it to panning. This is not always the case for parallel viewports. For example, if I double click out and go back into the perspective view, we can go to the properties, which will just be the viewport and camera properties for now, since we have nothing in our scene. And we can see that it's a perspectival projection. So I right click and I orbit, I hit shift and right click to pan, and then I can scroll with the scroll wheel. Or sorry, zoom. I can zoom with the scroll wheel. If I click on this drop down, I can change the projection mode to parallel. But since this is a non-elevational or still a 3D view, I right click to orbit still, and I hit shift right click to pan, and then to zoom, I use the scroll wheel. So those settings are still the same. If you're in a 3D viewport, it only changes when you go into an elevational or 2D viewport. The first geometry type we're going to look at is points. You can click on a point here or type point into the command line and then hit enter and left click the point. So right now our point is at the origin, which is 0, 0, 0. Each point is defined in the X, Y, and Z coordinate space. So if I move it, right now we have grid snap on down here. So I've moved it 1 unit in the X direction. So it is now 1, 0, 0. If I move it with this gumball and left click and drag the arrow, I think I actually moved it 2 units last time. So now it is 1, 1, 0, and then if I move it up in the Z, it is 1, 1, 1. If I hit Alt and then left click and drag this point, I now have 2 points, which defines a line. We can type line and click between those 2 points to define that line. So now we have 4 line segments, which if we join them, make a polyline curve, which is a degree 1 curve. I can delete that and instead just type polyline, or select the polyline icon in your toolbar to the left, and then left click on each of these points and hit enter. And now we've created an open degree 1 polyline curve. Type curve, then click on degree, and first I'm going to type 1. Now, if I click on each of the control points of this polyline, we'll notice that we now just have 2 polylines. That's because a polyline is a degree 1 curve. So a degree 1 Bezier curve is also a polyline. This type of curve geometry we're going to create is called a Bezier curve, which is defined by drawing tangential lines between divided points of each line segment. This will make a little bit more sense if we do it. So we're going to start with the first point on the first segment and draw it to the first point on the second segment, and continue this pattern, the second point to the second point, the third point to the third point, and the fourth point to the fourth, and then the fifth to the fifth. Now, if we type curve and then change this degree to 2, we can then left click on each of the control points, and we can see that what we first drew was the tangential lines that define this degree 2 Bezier curve. Now, for a degree 3 Bezier, it's going to be the same process, but we're going to repeat it recursively. So in this case, 2 times. So I'm going to start by changing this layer. So select the object, and this will just keep this demonstration a little bit cleaner. So now we can draw each of the lines between the control points in one segment to the control points on the next. So that would be a degree 2. Now, to make this a degree 3 Bezier, we just need to do this process again, but on the curves we just drew. So type rebuild, and now we are going to draw lines between each of these segments. Now, if we make one new layer for the resulting curve, we can double click and make sure that we've done it right by clicking on this curve icon or typing curve, changing the degree to 3, and drawing out a degree 3 Bezier curve. The next geometry type we're going to look at are surfaces. One way that you can produce surfaces inside of Rhino is defining first curves and then defining certain relationships between those curves, which can be used to define surfaces. One option for generating surfaces is the loft command. So we can type loft, gives us some options. These are going to be fine for now. We can hit OK. And then if we switch our view to shaded, click on the arrow drop down and select shaded, we can see that it has drawn a lofted surface between these 2 curves. Effectively, a lofted surface is a type of ruled surface in which one curve is infinitely divided and drawn to the correlating control point on the next curve. So this is similar to the definition of the Bezier curves that we just looked at, but instead defining a surface instead of a curve. We can actually show this by rebuilding each of these. For this demonstration, it's going to be best if we rebuild and then change this to a degree 1 curve so that the control points align with what we're trying to draw. And if it's helpful, you can either turn the points on so that they're visualized. So just click this tab here. And then we're just going to go through and draw lines between each of these points. There are 3 primary types of surfaces. The first is a planar surface. So if we type rectangle, we can click 2 points to draw any rectangle. And if we select that rectangular curve, we know that it's a 2-dimensional curve because we just drew it, a flat rectangular shape. So by typing planar surface, we can generate a planar surface from that curved boundary. So because we've generated this with planar surface, we can be sure that this is defined only in 2D space, which means any two-dimensional method of fabrication like laser cutting can be used for this surface. All you need is the edge definitions of the surface. The second type of surface is a singly curved surface. So a singly curved surface is any surface that is defined by a curve in one direction. A sweep can be defined by a rail curve and a profile or section curve. So if I draw a straight line, draw another line vertically, type sweep 1, it's prompting me to select the rail curve, and then the sweep shape. I'm going to hit enter, OK, and we can now see that we have generated a planar surface defined by this vertical sectional curve and this horizontal rail curve. If we wanted to make this rail a curve instead of a line, and then we try that again, we've now made a singly curved surface. It's only curved in one direction. In this vertical direction, it's not curved because we're using a straight line as the sectional profile. If we type rebuild on that sectional profile, use a degree 3 and then 5 control points, hit OK. We can then add curvature to this sectional profile. And then when we type sweep 1, we can select the rail, the sectional profile, and we now have a doubly curved geometry. It's actually curving in the YZ plane as well as in the XY plane. So this is producing a doubly curved surface, which is difficult to unroll, impossible to unroll without deformation. So this makes it more difficult to fabricate this type of geometry. And then I'll generate those same two examples again. So to the right, we have a planar surface, then a singly curved surface, then a doubly curved surface. If we want to check this ever, what we can do is go to Analyze. So if we ever want to check the degree of curvature of these surfaces, we can just select all of those surfaces, go to Analyze, Surface, Curvature Analysis, and then just make sure you go to Gaussian and then select Auto Range. And we can see that we have some problematic areas for fabrication that include excess curvature. One of the things that you can do with singly curved surfaces that you cannot do with doubly curved surfaces is you can type unroll surface, hit enter, and it unrolls into a flat surface. So we could laser cut or fabricate using 2D manufacturing methods this flat surface and then bend it into this singly curved shape. We can also do that with planar surfaces, although there's no need to actually transform them. It just orients it at the origin. However, if we try to do this with doubly curved, it gives us an error saying unrolling doubly curved surfaces will produce inaccurate results. So we would have to use another type of unrolling that uses or allows for deformation in the surface, which isn't always ideal for manufacturing. The next type of geometry we're going to look at is similar to a surface. It's actually just made up of multiple surfaces, which is called a polysurface, or in Grasshopper, it's called a boundary representation surface, or BREP. The quickest way to do this is to type something like extrude surface, and then we can type D, click one point and the next point, and then extrude. So we've just extruded that surface into a closed solid poly surface. The other option is to offset. So we've just offset that surface into a closed solid poly surface. But we can also produce solid objects by just typing things like box and clicking 3 points, and it will produce a box. We can also type sphere to produce a sphere, cone to produce a truncated cone. So all of these are going to be considered boundary representational objects when we move into Grasshopper. With these polysurface objects, only if they are closed solids, which all of these are because they're primitives, you can use Boolean operations to subtract, unify, and intersect them. So if you type Boolean union and click on two objects and hit enter, we can get these two objects unified. Select first the object you want to subtract from, and then the object you want to subtract with, and then we can just delete that. We see that it's removed that volume from the overall solid. If we continue doing this, it's going to make each of these faces messier and messier as we continue, and eventually it will not Boolean any further because the surfaces will be too messy. So to clean this up, you can type merge all coplanar faces, and it will merge anything that is coplanar and aid in kind of just keeping your model clean as you go through the Booleaning process. So now the last one is to just type Boolean intersection, select both geometries, hit enter, and it gives us the intersection between those two volumes. The last type of geometry that we're going to discuss differs from surfaces in that it is defined by vertices, which are points in space, and then the edges between those vertices, which are just lines connecting each of those points in space. And then those construct a series of faces that are actually what we kind of visualize. So this type of geometry is called a mesh, whereas surfaces are defined mathematically, as we saw and discussed, relating to Bezier curves and then the development of surfaces mathematically. One nice thing about a mesh is that it's lightweight computationally, so it is efficient to compute. That's because it is made up of discrete entities. There are only a fixed number of points versus being mathematically or infinitely defined. To create a mesh, we can type mesh plane and then click 2 points. This is going to define a mesh plane in space. Right now we can see this grid is projected onto it. If we actually click on this point icon, show object control points, then we can see the control points here and select them and move them. And we can move them however we like, but as we move each of those control points or mesh vertices, it will adjust the faces and edges as well. Similar to polysurfaces, we can make mesh primitives by just typing mesh and then box, mesh and then sphere, and then mesh cone. As I mentioned, since the polysurfaces are mathematically defined, and these are discretely defined by their vertices, edges, and faces, the resolution matters and can be defined by you, the user. So when we do that again, we can type mesh box, hit enter. It actually prompts us to input the resolution. Right now it's 10 by 10 by 10. If I change this to 1 by 2 by 2 and then redraw the box, we can see that in 2 axes, we have 2 divisions. So there are, in this case, 4 faces on this side of the box. Here in this axis, there's only 1 division. So there's only 2 faces on that side, this back side, and the top and bottom. You can do this with each one. So the mesh sphere as well, but this one prompts us to select the faces around the sphere and the vertical faces. So we can increase this to get a higher resolution sphere. And as you continue to increase this, so let's say 40 by 40, it will approach the kind of resolution of an actual sphere geometry. But as you increase the vertex, edge, and face count, respectively, it will continue to increase the computational load. We can also do Boolean operations with meshes inside of Rhino. So if I just copy these, we can start with a mesh Boolean union, and it combines those, and then a mesh Boolean difference, and subtract that. Rhino doesn't handle mesh Booleans as well as BREP or polysurface Booleans. So just be careful, eventually you will get errors. There are other modeling software like ZBrush, which can handle better mesh Boolean operations, but Rhino definitely privileges surface or volumetric modeling with polysurfaces, surfaces, and curves over meshes, but meshes are extremely lightweight to compute, so they're beneficial in terms of 3D programming. Okay, that's it for the introduction to Rhino's interface and geometry types. Next, we're going to get into an introduction to Python, including variables, conditionals, loops, and functions.